Hello, everyone, and welcome back to your channel of basic engineering. Uh, we stopped last time at the dry friction. We talked about the equations of equilibrium and the friction, how it's related to the force applied. What is the relationship between that and the normal force at the point of impending motion? And today, we are going to take two more examples. Last time we had an example where the surface on which the crates were sitting was horizontal. Today we have an inclined surface and we see what's the difference and how to use those. So in this problem, we have, again, an inclined surface with two blocks, a small one A and a bigger one B. They're connected by a flexible cable, and this cable passes around a frictionless pulley. There is no friction, meaning the tension on both sides is the same. Of course, there is no such thing as frictionless pulley, but we mean the friction between the belt and the pulley is so small. Because if it weren't small, um, we have to apply other rules or another equation that we are going to cover next time. So when we do the belt friction. So after that, they give you the coefficient of static friction between the two blocks to be 0.25. And then they said, and the point of impending motion. So if this bottom block is about to slide down and the upper one is sliding, of course, up, what would be the coefficient of friction between the block and the surface? Meaning, if it's too low, this thing would slide. If it's too high, then it won't budge. But what is the value that would make the motion impending? Meaning, just if you come and blow on it, it will start sliding. That's basically very small force, extra force would let it slide down. And the angle here between the horizontal and the inclined surface is 35 degrees. The blocks are 20 kilogram and 80 kilogram mass, each one of them. So of course, since the bottom one has a lot of unknowns, there would be the normal force from the top, the normal force from the surface, the friction force on the top side, the friction force on the bottom side, as well as the tension. 5 unknowns with 3 equations, it's impossible. So that's why we always start with the one that has at least a free side, because it will contain 3 unknowns: the normal force, the friction force, and the tension. So with the 3 equations of equilibrium, I can find those. So let's start at the very beginning here. We draw a free body diagram of the top block, block A. Okay, we don't have to draw it to scale, of course. It's an angle of 35 degrees, so how can we do that? We are going to waste time. So basically, I'm going to draw just a rectangle. In fact, it's a small one, but I draw it big. Doesn't matter. Because the dimensions of the block are irrelevant, really. So we say here is the center of mass for block A. So there must be a weight going down. There would be a normal force. We don't know its location, but it doesn't matter since we don't know the dimensions of the block. So even if we know where it is, it really won't help us. This block will never tip over. Like if you pull it, it will not tip over. How do I know? Just because they didn't give me the dimensions. If they did, then I have to check. But here it's impossible to know, right? So you know that is irrelevant. Now this weight, we said 20 times 9.8, so that's 196 Newton. Then we have a tension of on the cable here. Tension meaning going away from the body. And what else? Yes, you said it. If this bottom block is going to slide down, then the top one will be sliding up on the bottom crate or block. So since it wants to move up, the friction will be going down. and we're going to refer to that as A sub F. Here we have four forces acting on the block. Only one of them is, well, we can use X and Y as the horizontal and vertical, but I prefer to use X as the inclined surface and Y as the normal to that. Just because you see that if I use the Y, I will only have one unknown. But if I use the X as the horizontal and the Y as the vertical, these three guys have X components and Y components. So my equations will have to be solved simultaneously, which I don't like, okay? This angle they give you is 35 degrees. So this angle also is 35 degrees. Of course, not drawn to scale, but this angle is 35 degrees. How do I know? Because that was basically an angle that looked like that, and I turn it 90 degrees. So basically here it is. So that's the inclined surface and that's the horizontal. When you turn them 90 degrees, the incline would be the normal and the horizontal would be the vertical. So the angle between these two will not change if I rotate them both by the same angle, right? That's confusing in the beginning to many students, but it's really so easy to see that we took this angle and we turn it 90 degrees so it stays the same. Okay, the first equation we can write, even though we cannot solve it now, is to say they tell you that the coefficient of friction or static friction between the two blocks is 0.25. So I can write A sub F equals 0.25 A sub n. And then once I find A sub n, I will come back and calculate that. Notice that the X has T and A sub F. It has two unknowns, but the Y has only one unknown. So it makes perfect sense to start with the summation of the forces along the Y-axis and equate that to 0. I have A sub n going up, and the cosine of 196 cosine 35 degrees equals 0. So A sub n equals, we already have the 196, so we multiply it by cosine 35, and we get 160.55 or 160.6. Okay, 0.55 Newton, and it's going in this direction. Then I can come back here and multiply it by 0.25 or divide by 4 and get this to be 40.14. Okay, 40.14 Newton. It's in that direction. And finally, I do the summation of the forces along the x-axis, equating it to 0. You see 3 equations in 3 unknowns. So now I have, in this direction, I have A sub F, which is the 40.14, plus 196 sine 35. Both of those are pointing to the right, which is the positive x. The t is going to the left, so minus t equals 0, or if I add t to both sides, I can say t equals that. T equals that. Okay, I just moved it, so we don't have to write it twice. So here is the 40.14. I'm going to add to it 160.55 times sine 35. No, it's not I'm sorry, it's not 160. It's 196, sorry. 196 cosine 35 plus the friction. Yeah, that's correct. No, it's sine 35. This right. What's going on? 196. I said sine and I typed cosine. Plus, wow. Sorry, guys. Seems it's too late. Okay, so the tension equals 152.56 Newton going in that direction. Okay, So now we found all the forces acting on the top block. Now we draw the free body diagram of block B, the bottom one. Okay, let's be careful when we draw. So I have a block. Let's say roughly 90 degrees. Let's see now all these three forces that we found, be it A sub n, A sub f, or the tension, they are all internal forces. They come in pairs. Okay, equal, opposite, collinear. I hope you don't get bored by me keep saying that. It's extremely important. Okay. The first thing we found was A sub n going up, so there is an A sub n going down here of magnitude 160.55 Newton. Then I have A sub f was going down, so here I would have A sub f going up, again 40.14 Newton. Then I have the weight of the bottom block, 80 times 9.8, 784 Newton. Then I have a normal force going up, which I don't know its magnitude. So I'm going to call it B sub n. This block wants to slide down, so there is a B sub f opposing that. And finally, I have the tension keeping this from falling down, so pulling it up, always going away from the element to represent tension, which I think it's 152.56. We did it 3 times because I entered the wrong numbers. Okay, notice here they want you to find the mu sub s between the block and the surface. And we know that B sub f, equals B sub n plus, times mu sub s. So if I want mu sub s, I will have to divide Bf by Bn. We can find those easily from the summation of the forces in the x and the y. This angle is 35 degrees, just to be complete. So now I don't have to care which equation I start with. If I start with the summation of the forces in the x, I have 784 sine 35 is positive. I have the 152 is negative, so minus 152.56. I have the 40.14 is negative. And I have the BF is negative, minus BF equals 0, so I will bring the B sub F here and equate that to the rest. Instead of saying minus BF equals 0 and then rewrite it again, saving time. I hope we don't do it like last time. We save time and do it wrong. So we're going to multiply that by sine of 35, and then we're going to subtract the tension, and then we're going to subtract the A sub F or the B sub F. A sub F, which is the 40.14. And that gives me 257 Newton. And it's going in that direction. I don't care really, but because forces are vectors, it's better to show either the direction or the angle that it makes, which is the 35. So you can do this and write 35, or simply show that we know that it's 35. Summation of the forces in the y equals, because really nobody asks you what is the B sub F, so I don't care. I just need the magnitude, because that's what I'm going to divide by the magnitude of B sub n. When I do the summation of the forces in the y, I have B sub n going up, And the rest, this is going down and this is going down. So I can say equals and I add them together again instead of rewriting it twice. So I'm going to say equals 160.55 plus 784 cosine 35. So 784 cosine 35 plus, and then I go back all the way until I find the 160. Here it is, which is the tension. I get 802.77 Newton in that direction. And finally, mu sub s, which is the coefficient of static friction between the block B and the inclined surface, equals B sub F over B sub N equals. So I get the 257 divided by the 802, and that gives me almost 0.32. And that's the answer. So we had to start analyzing the top block, inverting A sub N and A sub F on the bottom block, calculating the tension, and then finding the B sub F on the bottom so that, and B sub N, so that we can find that, the coefficient of static friction. Finally, I have another example before we do another session or two sessions probably on belt friction. This one is nice. I liked it in the book, so I copied that. Let me clear the screen here. We have a boy that is pulling a sled with a box on top of it at constant velocity. How are we going to treat that? Well, if it's at constant velocity, meaning same speed, same direction, there is no acceleration, right? So we can use the coefficient of kinetic friction between the sled and the icy surface. This icy surface is making 15 degrees with the horizontal. The mass of the box and the sled is 50 kilogram, and this poor guy is only 40 kilogram of mass. He's pulling it by a cable or a rope that makes 25 degrees with the sled, with the inclined surface, meaning 40 degrees with the horizontal, if you use X as the horizontal. And they want you to find, they give you the coefficient of kinetic friction between the sled and the icy surface to be 0.05 or 1/20th, 1 over 20, very small. And they want you to determine the minimum coefficient of static friction needed between the boy's shoes and the icy surface. Why did they say static friction, not kinetic friction? Yes, because the boy will not be sliding at constant velocity, or else he will be going down, right? You see that when the boy places his foot on the icy surface, it's static. And we want to find, of course, we have to find a large coefficient of static friction between the shoes and the ice so that he wouldn't fall down, right? So we are going to analyze the sled first to find the tension in the cable, and then we analyze the buoy to find that coefficient of friction. So now instead of having two blocks on top of each other, we have a person and a sled, and the cable is connected between them. Of course, we will have to start with the sled, right? So we draw the free body diagram of sled and box. It's only 15 degrees. So here is the block with the sled. So we have the weight going down, always vertical, and the normal force going up. And then if we call this this block, the sled and the box, we call it A, then this would be A sub n. The sled is sliding upward, so there would be A sub f going down. This angle, we can draw it even here so it doesn't be cumbersome here. 15 degrees, which means the angle between the normal force and that is also 15 degrees. And finally, we have a cable that makes an angle of 25 degrees with the sled. So this angle right here, that's a tension, and that's 25 degrees. Like we said before, here, no matter what you do, if you use x as horizontal and y as vertical, or you use x as inclined and y is the normal, you will always have to solve two equations in two unknowns simultaneously. There is no way you can find one equation at a time, which we like because it's easier. But sometimes you will have to do it the hard way. Okay, as we always say, the first equation we can write right off the bat is that A sub f equals 0.05 A sub n. So the A sub n is 20 times as much as the friction force because that's the coefficient of kinetic friction the body is moving. So it opposes with a light force, much lighter than if it's at rest. Okay, we didn't specify. This is a 50 kilogram times 9.8, so this is 490 Newton going down. Okay, so we can start with any equation, either x or y. We will have to do both anyways. So if we do summation of the forces in the x direction and equate that to 0, in the x direction, we have t cosine 25 degrees. Going to the right, minus 490 sine 15 minus AF equals 0. So instead of saying minus AF equals 0 and then move AF to the other side, I can write AF on the left-hand side, or better even, write it 0.05 A sub n equals that. You see that? This basically was minus A sub f equals 0. And then I will add A sub f to both sides. So A sub f here would be deleted and it will show up here. But because I don't, there are only two equations, why write three things? So instead of A sub f, I write it 0.05 A sub n. Then we do the summation of the forces in the y direction equals 0. Doing the same thing, I'm going to say A sub n, and then anything going up would be negative, anything going down would be positive because I moved A sub n. So here I would say 490 cosine 15, that's positive. And t sine 25 is negative, minus t sine 25 degrees. These are the two equations in two unknowns. Notice 0.05 is 1 over 20, okay? So if I multiply the top equation, both sides, by negative 20, the left, so this equation comes here as negative A sub n. Do you see that? When you multiply it by negative 20 over 20 is negative 1, meaning negative A sub n. I multiply that by negative 20, so I get negative 20t cosine 25 plus 490 times 20 sine 15 degrees. Now, if I add these two equations together, I get rid of the A sub n and I can solve for the tension. Notice I don't care about A sub n and A sub f because they are not going to be inverted on the buoy, of course. They are inverted on the ice, and I'm not going to analyze the icy surface. Why would I? Right? So these two give me 0. And then if I take negative sign outside, negative something times t, this would be sine 25 degrees plus 20 cosine 25 degrees times t. And then if I factor 490 here, I say plus 490 times cosine 15 degrees plus 20 times sine 15 degrees. Now, if I want to solve for for t, I'm going to move it to the left-hand side so the negative becomes positive, and then I'm going to divide both sides by that. So I get t equals the right-hand side cosine 15 degrees plus 20 sine 15 degrees divided by sine 25 degrees plus 20 cosine 25 degrees. A lot of math, right? Hopefully we did it correctly. Let's calculate the tension. I'm going to open parentheses for the numerator, 490 times another parentheses, cosine 15 plus 20 sine 15, close, close, right? I'm going to close both. No, I think there is one more. We did the 490. No, 490 and then cosine. So I open two parentheses. Well, for the calculator, it doesn't matter even if you close one. Oh, but that's a numerator. And then between parentheses in the denominator, I say sine 25 plus 20 cosine 25, close the parentheses, 162.26, 162.3 Newton, and it's pointing in that direction. Okay, that gives me the tension in the cable. So let me, we don't have enough space, so I'm going to draw the free body diagram of the buoy here. I'm going to say free body diagram of the poor boy who's, trying to survive here. Here's the boy. He's pulling the cable that makes 25 degrees with the incline. I'm sorry, this angle is 25 degrees, and this tension is 162.3. He's standing on the incline, and the incline is making an angle of 15 degrees here. His mass is 40 kilogram. So 40 times 9.8, 392 Newton. Normal force is going through his head. B for boy, B sub n. My question to you, which direction is B sub f? Be careful. If you are trying to climb an incline, once he puts his foot on the icy surface, how does his foot want to slide? Forward or backward? Definitely backward. So the friction is opposing that. Notice here the sled was moving up, so the friction is going down. But here, the boy, his foot is sliding backwards, so B sub F is going up. This is extremely important to understand. So we don't just place them haphazardly, or you have to think a little bit. Now, like I did in the previous problem, I would be writing two equations of equilibrium, one in the x, one in the y, and then dividing the x by the y to find the coefficient. So it's almost identical to what we did there, except that there is no a sub n and a sub f inverted on the boy. Okay, so let's write the equations of equilibrium. Oh, I'm sorry. Summation of the forces in the x equals 0. In the x direction, I have b sub f going to the right. Notice I will do the same as I did before. I would say equals. Everything moving to the right, I would make it negative. Anything to the left, I would consider it positive. Uh, Again, this angle is 15 degrees. So I don't have anything going to the right. So really BF would be the 162.3, which is going, that makes an angle with 25 degrees with the incline. So cosine 25 plus 392 sine 15. That's all, right? Because the third force, Bn, is along the y. It doesn't have an x component. And when you calculate that, I'm going to take this number, cosine 25, plus 392 sine 15 equals 248 and a half. 248.5 Newton is going up the incline like that. And then summation of the forces in the y equals 0. I have b sub n going up, so anything going up after that would be negative. Anything going down would be positive. I have the 392 cosine 15 degrees, right? Cosine. Plus, because that's going down, plus the 162.3 sine 25 degrees. And again, 392 cosine 15 plus the 162.26 sine 25 equals 447.2 Newton, and it's going up like that. Finally, the coefficient of static friction for the shoe would be this over that, this number divided by that number. Wow, 0.555, meaning 0.56. Next question is, what is the price of that shoe, right? So really the shoes must be having a huge traction, very high coefficient of static friction with the ice, so that the poor guy will not fall down and slide backwards and, have to start all over again. Okay, I think that concludes the dry friction. I will, after we do the belt friction, I will try to find a problem that combines both friction types of frictions, and maybe even uh slipping versus tipping. So I will try to combine everything in one big example. But let's see what I find. Okay, that concludes the dry friction part. I hope you get it all. We did like 3 examples plus an explanation or a discussion on why these laws are the way they are. I hope you got that. If you have any questions or any comments, please don't hesitate to drop me a line and I will get back to you as soon as I can. Thanks and have a great day.